Hello, everyone. Today we are going to work with integration of rational functions by partial fractions. Uh, so guys, first, what are rational functions? Rational functions are like fractions with polynomial in numerator and polynomial in denominator. For example, x plus 5 divided over x squared plus x minus 2. Typical rational fraction. So polynomial in numerator, polynomial in denominator. What are partial fractions? Don't confuse it with integration by parts. By parts, we are using like the idea of derivative, right, of the product. Here, guys, we are going to represent more complicated rational fractions through simpler ones. How? First, let's look at sum of two simple fractions. Let's imagine that we have one fraction, 2 divided over x minus 1, and the second fraction is 1 divided over x plus 2. What I'm going to do, guys, I'm going to bring these two fractions to common denominator. Means that, well, just because we have two different denominators, I'm going to multiply my first fraction by x plus 2 and my second by x minus 1. So 2 x plus 2 minus, and that's supposed to be 1 by x minus 1. I'm not going to multiply 1. I'm just going to copy x minus 1. What are we going to have in denominator? I'm going to write it down as product of two binomials. We're going to simplify it later, but let's see. First, I'm going to work in numerator. So if I open first parenthesis, I'm going to have 2x minus 4 plus 4, sorry, plus 4 minus x, second parenthesis, plus 1. And I'm going to do the same in denominator. I'm just going to use FOIL here. So I'm going to have x squared, x by x, right? Plus 2x minus x and minus 2. So in numerator, what I'm going to have? I'm going to have 2x minus x, just x, right? And 4 plus 1 is going to give me 5. In denominator, I'm going to have x squared, and then x minus x is going to give me just x, 2x minus x, right? And minus 2. Now, guys, I'm going to ask you to compare the fraction I have over here and the fraction I was using as example of a rational fraction. You see that that's the same fraction. What are these two fractions? They are called partial fractions. You see that they're simpler. If my major fraction had a quadratic trinomial in denominator, each of these two little fractions have just binomials and they're linear binomials. Well, our goal is going to convert bigger fractions into smaller. And then I'm going to explain why do we need smaller ones. So how do we go backward if we kind of given the bigger one and want to get two smaller ones? Well, guys, basically, to go backward, well, here we just simplified everything, right? But before we simplified everything, our denominator was looking like a product of two binomials, x minus 1, x plus 2. How do we get these two binomials from denominator? Well, you know that we can always factor it. If you factor this expression, you are going to have x minus 1, x plus 2. And we do know how to factor, so it was easy, right? What else do I have? I also have 2 multiplied by x plus 2, which is one of these parentheses, right? And minus 1, let's write it, minus 1 multiplied by x minus 1, the second one. So it looks like I kind of have denominators over here, which are built from factors of denominator. And in numerators, I'm just going to have two numbers. The only question is what numbers I'm going to have in numerator. Like, how do I know it's going to be 2 and minus 1 and not 3 and minus 5? Well, the method of finding these numbers is called the method of undetermined coefficients. And let's do it once on this fraction so to get the idea of this method. Let's imagine that we don't really know that the fraction can be represented as 2 over x minus 1 and 1 over x plus 2. But because we can factor denominator already, I'm just going to write it down in factored form. we can try to think that it was like a sum of two fractions with unknown number on the top. Let's imagine that we don't know it's 2 divided over x minus 1 and unknown number on the top of the second fraction. Why I can assume this? Well, if I bring this to common denominator, I'm just going to have my denominator, right? And if I simplify expression like this, which for a and b I am going to figure it out eventually, to have like linear binomial, because it's kind of linear binomial by number, linear binomial by number. I add them up together. I'm just going to have linear binomial. Now the question is, what is a and what is b? What I'm going to do, guys, I'm going to start bringing it to common denominator again. Just I'm not going to simplify everything. So common denominator here is again x minus 1, x plus 2. So I'm going to multiply my first coefficient a by x plus 2 and my second coefficient b by x minus 1. Divide by x minus 1, x plus 2. And now I'm going to open my parentheses here in numerator and keep my denominator because I do know how it's going to look. I don't need to repeat the procedure. In numerator, guys, we are going to have ax and bx. I'm going to write it down like this. A plus b multiplied by x. I'm kind of taking x from both terms, ax and bx outside. And the last term is going to be 2a minus b plus 2a minus b. Now, what I'm going to do, guys, sorry, my plus doesn't look like plus. I'm going to compare my original numerator and my numerator with undetermined coefficients. And I'm going to say, well, denominators are matching. If I open my denominator here, I'm just going to get x squared plus x minus 2. I already checked it. So my numerators must be the same, well, unless I want to get a different fraction. So how do I make them the same? Well, I can kind of set up that coefficient of x is equal to 1, just because it equals to 1 over here. And coefficient of x to the power of 0 is going to be equal to 5, right? If I do this, if I can find a and b which are matching this, like numbers 1 and 5, then my fraction is going to be exactly original one, and I'm going to have no problems. How to find these numbers? Well, if I write down these two statements as equations, I'm going to have a plus b is equal to 1 and 2a minus b equals 5. And what I have a system of two equations with two variables. Not difficult to solve. You can use substitution or just elimination. I'm going to add these two equations together and get like 3a equals what? 6. B and minus b are going to make 0. And a from this equation is going to be equal to, right? And if I plug this 2 into my second equation, I'm going to have 2 multiplied by 2, which is 4, minus something gives me 5. 4 minus b equals 5. Obviously, b is going to be equal negative 1, right? Actually, 4 plus 1 is equal to 5, so b equals negative 1. So I found my coefficients, and they are 2, I'm going to write it down over here, and minus 1. Let me write them down over here, 2 and minus 1. And if I compare actually the decomposition with coefficients 2 and minus 1 to what I had originally, I'm going to see, yeah, they are actually 2 and minus 1. So I actually found the coefficients they had initially. So the method is called undetermined coefficients because first we assign like undetermined coefficients to our fractions, and then we find them using systems of equations. Okay, so that's how we do partial decomposition. Now, the question is, why do we need to do partial decomposition? To learn that, we are going to review a couple of integrals, which you'll kind of remember, but let's just kind of review, refresh. So number one, what is integral of 1 over x dx? We remember that it's a ln of absolute value of x plus a constant, right? What is going to be integral of 1 over x squared dx? It's not going to be ln of x squared, guys, right? Very typical mistake students are doing. They think that everything in denominator is going to result in ln. No, this one is the power function, x to the negative 2, right? We integrate it as a standard power function. We add 1 and divide by whatever coefficient is. And in our case, it's going to be x to the power of negative 1 over negative 1 plus a constant, which is going to result into 1 over x plus a constant. You see, it's not ln. Okay, what is integral 1 over 1 plus x squared? This one is a table integral. We learned this integral when we were doing inverse trigonometric functions. And actually this one is tangent inverse of x. I hope that you guys still remember it. Now you'll probably tell me like, oh, how these integrals are connected to our fractions. Let's try to integrate our first small fraction. Let's try to integrate our first small fraction, 2 over x minus 1. So let's try to calculate integral 2 over x minus 1 dx. Comparing it to integral of ln, we're going to see that if you make a simple substitution, u equals x minus 1, du equals dx, we are going to have 2 du divided over u, and that's going to give us ln, 2 ln of u, absolute value, which is going to result in 2 ln of x minus 1. So guys, if you understand how x minus 1 is going to appear in the final answer, you don't need to do substitution u. Linear substitutions usually are very easy to just understand, you see? So if you deal with simple fraction, you don't know the answer. Like a similar way you can calculate the answer for the second fraction, right? But if somebody is asking you to calculate the integral of this one, then what we are going to do, split it into two integrals and then calculate each integral separately. And yes, we are going to talk about this one and this one a little bit later when we have more complicated fractions, right? So what we did right now is called case number 1. So case number 1 is a special type of rational fractions which we decompose a certain way. I'm going to label it case 1, linear non-repeated factors. Linear non linear non-repeated factors. So why do we call them linear? Well, let's go back to original fraction. So we have, I'm going to write down again, x plus 5 over x minus, that was x minus 1, x plus 2, x minus 1, x plus 2. So why do we call them linear? Well, just because they are going to give us equation of a straight line. And sometimes, guys, x is going to have some coefficient. Remember, the straight line y equals 2x plus 1 is also a straight line. So those all are called linear. Why do we call them non-repeated? Each factor, like x plus 1, is going to be repeated only once in expression. So we're not going to have x plus 1 squared or x plus 2 cubed. Linear non-repeated factors. And that's how we solve them. Now, of course, if we have linear non-repeated factors, means that we eventually going to have nonlinear non-repeated factors and linear repeated factors. So actually these two words can be modified and give us different cases. Case 2, let me write it down, like how we consider it. We can have more factors in denominator, not just 2 factors. But the idea is going to be just write them down as simple fractions with denominators, which are kind of going to repeat each factor. Case number 2, repeated, linear repeated factors. What are linear repeated factors? Let's consider fraction. Okay, like this, x squared minus x plus 1 divided over x squared x minus 1. And somebody wants to calculate the integral of this. Should we do this? If you look at denominator over here, it's already factored, right? We do have 2 factors over x and x minus 1. Factor x is repeated. Let me underline it. Repeated. How many times repeated? 2 times. How my representation of the fraction is going to be different from this? Please watch. I'm not going to do the integral right now. I'm going to first decompose my fraction. X squared minus x plus 1 x squared x minus 1. Look how my decomposition is going to be different. Normally, guys, if x was not repeated, I would have a divided over x, my first like factor. But because we have x squared, we are going to add one more, b over x squared. And actually, if you have factor repeated 2 times or 3 times, you are going to add more terms. So here, 2 times 2 terms, 3 times 3 terms, 4 times 4 terms, and as many terms as you have kind of times. For the second factor, it's x minus 1 and it's not repeated. So we are just going to write down c over x minus 1. And instead of 2 indeterminate coefficients, we are going to have 3. Well, we solve this problem same way. Just going to bring everything to common denominator. What is common denominator? A. Well, what is missing for x? For x is missing 1 more x and x minus 1. So I'm going to write down a x minus 1. What is missing for b? Well, b already has x squared, so we are just missing x minus 1. And c is missing actually x squared, right? Very good. And denominator is going to be x squared, x minus 1. Remember, guys, when you look for common denominator, your common denominator must be equal to original denominator of the fraction. Sometimes people just multiply everything, all denominators. And if you do this, you are going to have x cubed denominator, which is not the case. Actually, original fraction has x squared. And it's supposed to be equal to x squared minus x plus 1. Right, guys? So, yes, here I'm going to show you a method of calculating this undetermined coefficients, which you can use sometimes, especially in like case 2 and sometimes in case 1 too. So please watch how I do this. I know that my denominators are already equal. This denominator and this denominator are same. I just need to make same numerators, right? Well, if numerators are same for sum a and b and c, it's supposed to be same for all possible x's. I'm going to pick up certain x's which are convenient for me and check if numerators are going to be same. I'm going to start with x equals 0. I'm going to pick up x equals 0. I'm going to plug it over here, and I'm going to have just 1, right, in numerator. And if I plug x equals 0 into first term, I'm going to get 0 x equals 0 into second term is going to give me minus b, and x equals 0 into third term is going to give me 0 again. And you see this, I already found coefficient b, it equals to negative 1. Why did it work? Because actually I'm using the root or 0 of my factor x square or x. And that's why I got the answer. Now, guys, because I have it repeated twice, unfortunately, method is not going to work when I plug it second time because I'm still going to get b minus 1, but I'll need to know a and c. But what I can do, guys, I can plug in x equals 1. X equals 1 solves equation x minus 1 equals 0, right? And let's see what we are going to have. X equals 1 is going to give me 1 minus 1 plus 1. Well, in total, it's going to be 1 again. 1 minus 1 is 0, plus 1 is 1. Here, on the right side, I'm going to get when x equals 1. The first term is going to turn into 0 because it has a parenthesis x minus 1. The second is going to turn into 0. And the third one is going to turn into just c. So I already calculated my c. c equals to 1. The only one left is going to be coefficient a. And unfortunately, if you look at expression, I used already 0 and 1, so I kind of cannot use them again. But I can use any other number here. Just because I already know b and c, I can use them actually into expression. And the only one is going to be unknown, is going to be a. Well, that's what I'm going to use. I'm going to use x equals 2. Again, 2 is just a simple number, which comes to my mind. So 2 squared minus 2. 2 squared is 4, minus 2 is going to be 2, plus 1 is going to be 3. X equals 2 for my first expression is going to give me a by 2, and 2 minus 1 is 1, right? Plus my b is equal to negative 1. I'm going to plug it in. And then x equals 2, 2 minus 1 is 1. And my c equals to 1, and 2 squared is going to be 4. You see, I again got equation for a. It's not that simple as equation number 1, equation number 2, but difficult to solve actually. So let's say I have 4 and here minus 1, so it's going to be actually what, 3, and 3 is going to cancel. Somehow I'm getting like a 0 for my coefficient of a, which can be true. Or I probably did a mistake somewhere. Let me double check everything. 2, 2 minus 1, 1, b equals minus 1. So this is 1. This is multiplication, not a minus. And 2 and 1. Hmm. Yeah, it looks like I'm going to just cancel this 3 and 4 minus 1, this 3. And my a is going to be equal to 0. Well, happens sometimes. So, yeah, guys, if you see that something is wrong with this equation, we can always fix it in class. So, so what do we have now? Now we have just two coefficients, b and c. A is going to be equal to 0. Right? What I'm going to do, guys, instead of a question mark, I'm going to continue solution of my equation. I'm going to write down that. I have b over x squared, which is going to be negative 1 over x squared, and the c over x minus 1 plus 1 over x minus 1 dx. And if it's very easy to find out what is going to be, right? We just integrated 1 over x squared, it's going to be minus 1 over x, but because it has minus already in front, it's going to be plus. And for the second one is going to be the logarithm, right? Linear substitution, x minus 1 is going to solve it. And we did the problem. So that's how we solve equations of case 2. Now, guys, of course, remember linear repeated. We have uh, linear non-repeated, linear repeated. Now we need to have non-linear. How we are going to have non-linear for case 3? Case 3. Irreducible, quadratic. Quadratic factor. What is irreducible quadratic factor? Let me first consider integral. Integral 2x squared minus x plus 4. And here x squared plus 4. Well, guys, if you look at this expression, you're going to see that this factor, x squared plus 4, you cannot factor it more because actually this is going to have no zeros. Remember that you can factor and each of the factors is going to have 0, like x minus a, x minus b. This one you cannot factor, or actually you can factor, but it's going to involve complex numbers. So factors like this, which are never equal to 0, are called irreducible quadratic factors. And they are going to work as just a solid fraction. So I'm going to consider that we have a over x. This one is a standard one. And for irreducible quadratic factors, I'm going to have two terms in numerator. Like this is a factor of second degree, then numerator is going to be first degree linear. We are still going to have 3 letters, but kind of equation is going to be a little bit more complicated. Well, let's calculate it, right? So again, we need to kind of bring it to common denominator. I'm going to put this little curvy lines to show that these are not integrals. We are just working with expression under the integral. So we have a x squared minus plus 4 plus bx plus c multiplied by x and divided by x squared plus 4. What are we going to have here after we open all the parentheses? A x squared, and we are going to have bx squared. So I'm going to write down maybe a plus b in front of x. A plus b. Then the first power of x is going to be only cx. And a multiplied by 4 is going to give me 3 term. Now I'll need to compare my numerator here and my numerator of original fraction. And I see that this expression on the top is equal to 2. C equals to -1. And 4 I think I forgot to multiply 4 by a when I was copying it. Let me make it like blue 4a. A multiplied by 4. And this term must be equal to 4 from where a equals to 1, right? So a equals 1, c equals -1, and a plus b equals 2 from where knowing that a equals 1, b equals 1, 2. Well, usually, I guess it's not going to be that simple, but that's my example. I kind of design it as I like it, right? So now I'm going to write down the final fraction over here. So a equals to 1, so it's 1 over x plus b equals to 1, it's x, c equals to -1, and x squared plus 4. And I'm going to put integral here, and that's going to be my expression. So that's how do we find the integral here? Well, first integral is simple. It's going to give us a ln, right? A ln of x. Everything is clear here. What to do with the second one? For the second one, guys, we are going to represent it as two integrals. Integral of x over x squared plus 4 dx and minus integral of 1 x squared plus 4. And let's first work with the first one, this integral. Guys, I don't know like if it's clear to you already or not, but you probably can guess that if we label u equals x squared plus 4, then du is going to be 2x dx. That's exactly what we have in numerator besides 2, right? So we can do substitution here, and that's going to give us du over 2, moving 2 over here, divided over u, which is going to give us 1 over 2 ln of u, or it's going to give us 1 over 2 ln of x squared plus 4. I moved my absolute value brackets from here just because x squared plus 4 is always positive. Okay, now let's talk about the second integral. Well, remember somewhere in the beginning I told you that integral dx 1 plus x squared is supposed to be tangent inverse of x, right? If you differentiate tangent inverse, you are going to get a you're going to get 1 over x, 1 over 1 plus x, right? What should we do with this 4? Well, we'll need to modify it a little bit to bring to the form without, like, instead of 4 have 1. Usually we take it outside the parentheses. So we use a green color. So I'm going to move over here and work on the integral a little bit aside. So what I'm going to have, I'm going to write down 1 over 4 and then 1 x squared over 4 plus 1 dx. So 1 over, it's like I kind of, if you multiply by 4 back, you're going to get x squared plus 4, right? Now, kind of looks almost tangent inverse, right? Just instead of like x squared over 4, we're supposed to have just x squared. Guys, if you don't see kind of substitution here, you can do it. If you see it, you can write down the answer. So we need to make sure that x squared over 4 equals to some kind of u squared, right? To turn it into tangent inverse. From where x over 2 equals u and dx over 2 equals du. If you plug everything in, don't forget about this 1 over 4, we are going to have, instead of dx, 2 du, in denominator, u squared plus 1, which is going to give you tangent inverse, right? So canceling 2 and 4, we are going to have 1 over 2 tangent inverse. And instead of u, I'm going to substitute what is my substitution, x over 2. That's going to be it. So we calculated our last integral. Now we need to combine the whole expression together. I'm going to continue right down into, so ln of absolute value of x. My second integral was 1 over 2 ln of x squared plus 4. And my last integral was, oh, I'm supposed to write down minus because there was minus in front of the integral. Minus, and where is it? 1 over 2 tangent inverse of x over 2 plus a constant, kind of long expression. What I want to say, guys, over here, that integral of case 3 usually uh, will have one ln looking like this and one tangent inverse. So tangent inverse is going to be the must term in case 3. Okay, you can have ln or not have ln depending on like what was your first factor. Like maybe it was x squared and then you are going to have ln and the power function. Maybe not. Maybe you're going to just have plain ln. But these two ln and tangent are always coming, almost always coming together. Okay. Or maybe in some rare cases, you are going to have only ln and only tangent inverse, but usually they're going to appear together. So guys, should we have case number 4 when we have irreducible, which is like x squared plus something, and also repeated? Yes, guys. We're not going to solve any problems on this case, but I'll need to show you how the case looks. So case number 4. Case number 4. Irreducible, repeated factor. Okay, I'm going to give you example. Again, we are not going to solve it. It's extremely long. I'm just going to show you how the composition is going to look, okay? Imagine that you have fraction 1 minus x plus 2x squared minus x cubed divided over x squared plus 1. You cannot factor x squared plus 1 because it has no zeros. And that's going to be actually this irreducible and repeated factor. Irreducible because it's x squared plus 1. You cannot factor it into linear factors. Repeated because it's squared. So we are going to represent our partial decomposition. Well, the first x is just going to give you a over x. The second is going to be bx plus c over x squared plus 1. And then dx plus e over x squared plus 1 squared. So the reducible repeated factor is going to behave like a repeated factor, just like you repeat actually reducible fraction for it. Okay, we're going to solve this problem. It's just like you will need to be aware of like that. Cases like this exist too, and they're supposed to be extremely long. Like even like a one irreducible repeated factor is going to result at least into 5 different coefficients. Now, guys, we're going to talk about some special cases of rational expressions. So let me move this up and consider special cases. And we're going to start with case number 1. What is going to happen when numerator, the power of numerator, is greater than denominator or equal? I'm going to show you example. For example, we have integral of x cubed plus x over x minus 1 dx. You see that the power of denominator is 1 and the power of numerator is 3, so it's obviously greater. What should we do, guys? We can always perform a long division. Use long division. Well, let me remind you how long division looks. You are going to copy your expression in numerator, x cubed plus x. And then you are going to write down, too low, sorry. Sorry, I want to erase it, but now it's erased. You're going to write down by what you divide. So divider, and the result quotient. So by what we multiply x to get x cubed? By x squared. So let's do it. By x squared, we're going to have x cubed minus x squared. Subtracted, like we usually do with division. Cube and cube subtracted like 0, and x squared subtracted is just going to give me x squared. It was with minus, now and extra minus, and plus x. By what we'll need to multiply x to get x squared? Well, by x. So we do multiplication by x of x minus 1, and that's x squared minus x. Do subtraction, And we are going to have 2x, x and square are going to disappear. And I still need to divide it until my power of numerator is less than denominator. So I still, by what we need to multiply 2x to get x? By 2. So I'm going to write down 2x minus 2. But this is the last step already. Minus minus is going to give me 2. So what I'm going to have, guys, I'm going to represent this fraction now like divided in divided form. I'm going to have quotient x squared plus x plus 2 plus I'm going to have the remainder, which is 2, and divided by x minus 1. And now I can put integral sign dx over here and integrate everything. In this case, it's easy just because I have an easy problem, but usually it's not going to be that easy. You integrate x squared, it's x cubed over 3, right? X is x squared over 2. 2 is 2x, and this one is going to give me 2 ln of x minus 1 plus a constant. And let me remind you that not always everything from denominator is going to become argument of ln. Actually, anything else besides linear factor is not going to become. Okay, so this is what we do when numerator, the power of numerator is greater than denominator. We put the power or the degree. But now, sometimes your fraction is not going to look like a rational fraction. And then we will need to turn it into rational fraction. So special case 2, rationalizing substitution. Imagine that we are dealing with integral dx over x plus 1 under the square root. You see, this is not rational fraction actually, because that's not a polynomial in denominator. Whenever it has a square root, it's not polynomial already. So we are going to do here a rationalizing substitution. So turn it into a polynomial, get rid of a square root. How? Usually, guys, we are trying to label the whole inconvenient thing as a new variable. So my substitution is going to be u equals square root of x plus 1. Then u square is going to be x plus 1. And um, maybe I'm going to solve it just for x. U square minus 1 equals 2x. And I'll need also dx, right? So if I differentiate it, I'm going to get 2 u du, sorry, 2 u du, and equals dx. Now I'm ready to plug everything into my expression. So in numerator, I have 2u du. In denominator, instead of x, I have u square minus 1. And then instead of a square root, I have u. Very lucky. I can cancel u from numerator and denominator. And my expression is going to look like this. 2 du over u square minus 1. Very good. What should I do with this expression? Well, I can factor my denominator, right? I'm going to have 2 du u minus 1, u plus 1 using the formula, right? Now, guys, because I'm doing problems like this for a long time already, I can guess how partial decomposition is going to look. We have case number 1 here, and my partial decomposition is going to look like this. Du over u plus 1 plus du over u minus 1. If we bring it to common denominator, this plus 1 and minus 1 are going to cancel, and u plus u is going to give you 2. Okay? Uh, so, no, u, that's supposed to be minus, sorry. So u plus. It's supposed to be minus. But this way it's going to work. So, just like imagine that you kind of bring it to common denominator. It's u minus 1 minus u minus 1. again. We are going to have two minuses in front, so you can put minus in front. Hey, I did it. I put them in reverse order. That's okay. You can do it standard way. 2 minus 1, minus 1, minus. Okay, now we're going to have two ln's, right? We're going to have minus ln of u plus 1 and plus ln of u minus 1, because two minuses, right? And I'll go back to original expression. One step. Minus ln square root of x plus 1 plus 1 plus ln of square root of x plus 1 minus 1. Guys, I'm going to combine these two ln's together. Remember that when we have a difference of two ln's, we can combine it into a fraction. ln square root of x plus 1 minus 1 square root of x plus 1 plus 1 absolute value and a constant. You can combine it or you can leave it as it is. No one actually going to complain if something does not look same way. Okay, so that's going to be rationalizing substitution. Why do we call it rationalizing? Well, it's going to turn expression which is not rational into rational, because this expression we have with x is not rational because it has a square root, and now expression without x is going to be rational. It's just a rational fraction for which we can use case 1 or case 2 or case 3. I think that's all for integrating by partial decomposition. And I'm going to put problems for solving, let me kind of self-solving problems. So problem number 1. I'll try to make up a problem for each different case of integration. So, and make them in order. What's this one? Let me do to make it in order. I'll need to use case 2 problem. 3x over x cubed plus 2x squared plus x. Problem 3, x squared minus plus 8 minus x plus 8, x cubed plus 4x dx. And the last problem, problem 4, okay, this is cube. It doesn't look like a cube. Let me write down 1 over 1 plus cubic root of x. Cubic root of x. That's all. And kind of practice with these 4 problems. Bring whatever your questions on Wednesday, and I'll see you, okay, in class.